Okay, now we'll talk about the electronic structure of atoms, and we first will talk about this equation that we use that interconverts the wavelength and the frequency of light. So in units of meters per second, speed of light is roughly 3.0 times 10 to the 8th meters per second. And this is, we define this constant as c. And then with that as a constant, when we're given either the wavelength or the frequency, we can use this equation to solve for the other. Okay, so you'll see this sort of problem. Some diamonds appear yellow because they absorb purple light of a frequency 7.23 times 10 to the 14th hertz. Calculate the wavelength of the absorbed light in units of nanometers. And so in this case, you have the speed of light. The problem is giving you the frequency. And frequency, for the purposes that it's useful for us to use, we replace this hertz with a per second. Okay, this is what this hertz means, is a cycle per second. So we take this and we put an s to the minus 1 here, and then those two cancel. This over s and this s to the minus 1 cancel, and we're left with a unit here of meters, and that's good because wavelength is a length. So we go through and we get 4.15 times 10 to the minus 7 meters. And then finally, we can do a conversion into nanometers. That's common for visible and ultraviolet light, is to put it in nanometers instead. So here we're dividing it by 10 to the minus 9, and that gives us 4.15 times 10 to the second power, or 415 nanometers. For anything that you're doing in invisible or ultraviolet light, you also can just think about moving the decimal place. If I move this over 2 spots, then this part becomes 10 to the minus 9, and so I can also just think about moving the decimal 2 places and changing this unit to nanometers. CD players use lasers that emit red light with a wavelength of 685 nanometers. What's the energy of 1 photon, and what's the energy of 1 mole of photons of this red light? And so convert the wavelength into a frequency. So the frequency is equal to the speed of light divided by the wavelength. And so 3 times 10 to the 8th meters per second. And you may notice this is not proper scientific notation, but your calculator actually will take this, 685 times 10 to the minus 9. And this gives us 4.38 times 10 to the 14th per second as the wavelength of, as the frequency of that light. So now if we take and calculate the energy per photon, we use this E equals h nu. H is Planck's constant, which I put in right here, and nu is the frequency that we just calculated. So 6.62 times 10 to the minus 34th joules times seconds per photon times 438 times 10 to the 14, which we just calculated. Seconds and seconds cancel out, and so we're left with an energy of 2.90 times 10 to the minus 9th joules per photon. And then at the end, though, if we want energy per mole, which is a common thing to want, we just take this number and we multiply it by Avogadro's number. Photons will cancel, photon and photons cancel, and we're left now with an energy of joules per mole. Okay, when I put this into the calculator, then 1.75 times 10 to the 5th joules per mole, or if we were to ask you to put it in kilojoules, you would take this number and divide it by 1,000, and it would give us 175 kilojoules per mole. Next in this chapter, we talked about quantum numbers, and it's important in a normal semester, we usually would have you memorize these. You just need to make sure that you understand what these are and have access to them. So these are permitted values of the quantum numbers. So n can have values from 1 to infinity, any integer, any counting number. L is constrained by the value of n. So if we're talking about n equals 2, then L can have values of 0 and 1, because L can only go up to n minus 1. And in the case of 2, 2 minus 1 is 1. M sub L has values of plus and minus L. It goes through 0 and plus and minus L. And so it is constrained by the value of L. And then M sub S can have values of minus 1/2 or plus 1/2. Okay, and so this is the kind of thing that you would see on the exam. You would be given, you'd need to spot the wrong electron configuration, would be one way I could ask the question. But all of these have something wrong, and let's see what it is. So if I look at this electron configuration, N's values start at 1, so N equals 0 is not allowed. Okay, and this one, L can have values up to N minus 1. So 2 minus 1 is 1, and so this L can have values of 0 and 1, but not 3. Okay, and this next one, N is okay. L is okay because 3 minus 1 is 2, so this can go up to 2, that's fine. M sub L, for this case, would have values of minus 2, minus 1, 0, plus 1, and plus 2, but not plus 3 because this only goes up to plus L. It would only go up to 2, and so, and then finally the N value is okay, the L value is okay based on the N, the M sub L value is okay based on the L. And this one, though, M sub S can only have values of plus 1/2 and minus 1/2, and so that's what's wrong with that last one. Also, in a normal semester, you might be asked to sketch these. I might instead ask you to identify the shape. So I might give you a shape like this and ask you, and you would need to identify this as a p orbital or something like that. This all builds up to doing electron configurations, and this is one way to think about electron configurations, where you would take whatever element that you're talking about and you would figure out how many electrons it has, and then you would start in the bottom box and you would go up, down, and that box is full, up, down, then that one's full, up 1 in each box, and then if you still have electrons you go down 1 in each box, and then if you still have electrons you go up to the next and go up and down. You also have, for the transition metals, we have a few exceptions that happen here. And here are those 2 exceptions. These are the only 2 exceptions that I will ask you to know. Is for chromium. For chromium, we might expect this to be 4s2, 3d4. But in fact, one of the 4s electrons jumps ship over into the 3d, and it is in fact 3d5, 4s1. And copper does something similar. We would expect it to be 4s2, 3d9. However, one of the 4s electrons jumps ship over into the 3d, and it in fact is 3d10, 4s1. And we don't talk about it too much in this course, but in my more advanced course we talk about half and completely filled orbitals are more stable, lower in energy. That's the reasoning for why these two do something strange. It's useful for you to think about the periodic table in this way. If you divide the periodic table, these first 2 columns as the S block, these last 6 columns as the P block, and then these middle ones as the 3D, 4D, 5D, 6D, it's a faster way to think about doing electron configurations. And here's what I said on the previous slide. I've just here taken and color-coded everything, where this is the S block, the P block, the D block, and the F block. All right, finally, let's talk about ground and excited states. And so for something like a carbon atom, remember we're going to have 6 total electrons, and we go to the first level and we go up, down, and then we still have more electrons, so we go up, down. We still have 2 more electrons to put in. And so when we get to a level like this, we go up, up, up before we put any down. I only have 2, so I went up, up. And when we're doing all that business, what we're doing is we're coming up with the ground state. If I didn't fill them in that order, I would end up with an excited state of that atom. So let's look at what some of those could be. So I took my 6 electrons and I went up, down, and instead of doing the ground state here, instead of going up, up, I go up, down in the same box. Well, this is allowed. This actually occurs. This is an excited state though. We have to take the normal ground state atom and heat it really hot or hit it with some strong light to cause this to happen. And there's an infinite number of ways of doing this. So this one, also different from the ground state. We've taken our electrons and we went up, down, down, and now up, up, up. So we took effectively this electron and moved it over here. But that also is another excited state. There's an infinite different number of ways of getting excited states. There's a third way. All of those, you will notice, are different than the ground state. The rules that we introduce right away are the rules to give you the ground state. Any other will give you an excited state. Here's kind of the only two ways that I can draw a not allowed electron configuration or forbidden electron configuration. One is this very strange looking where I sandwich a third electron into this box. Up, down, up. Okay, that's forbidden. This never occurs. Not even under really high heat, not even if the atom was on the sun. This electron configuration never occurs. It is impossible for it to occur to put a third electron in. And then the same thing here. This one never occurs where we've put two electrons in the same box. The problem here is we put both of them up. Okay, and what it ultimately comes down to is this thing called the Pauli exclusion principle that says each orbital can hold two electrons of opposite spins. So this has 3 electrons, so it violates the first part. This has 2 electrons, so it's okay with the first part, but violates the second part. The electrons right here have the same spin and not an opposite spin. Finally, you can be asked about paramagnetic and diamagnetic substances. So, for example, helium here, it has 2 electrons. The 2 go into the first box, up, down. So it has as many up electrons as down electrons. Whereas lithium has 2 up electrons and 1 down electrons. When we have unpaired electrons, which is what we would call this guy, this unpaired electron causes the atom to be paramagnetic. When it contains 1 or more unpaired electrons, it's attracted to a magnetic field. And like with helium here, if they're all paired, if every up has a corresponding down, then it's diamagnetic. Diamagnetic is weakly repelled by a magnet, and paramagnetic is strongly attracted to a magnet.